All right, so we are R24. We finished our project, and I think we got some really good insights. And let's see, we would like to share those with you and hopefully open up for some good discussion and questions. So our project is essentially trying to understand how all these challenges that we have been hearing about in rural transportation related to different, roadway features, lack of connectivity, things that are very specific in terms of weather, how these can affect the operation of self-driving cars. And I think, the last two presentations kind of sets up the stage very nicely because we heard about the need, the demand, and the challenges that users face in this community. And also in the first presentation, we heard about how different elements like deer on roadway and other animals and different kinds of, people, pedestrians just coming into the road, that makes rural transportation and rural driving more challenging. So we want to look at it from the perspective of autonomous vehicles and self-driving cars and how specifically these become a problem and how we can solve, or at least try to solve some of these things. So our project goal is we want to establish a digital twin-based simulation. So something that will let us test these things from the thank you.
The other side.
So yeah, self-driving cars are easier than auto sometimes. But anyway, so yeah, we want to do this where we want to set up a way we can test these things in the lab, with the safety of the lab, and still be able to get realistic responses from vehicles. So we don't want to entirely rely on simulations. So we wanted to establish the digital twin-based simulation and have an actual car that will give us the dynamics. So it turned out to be a really interesting exercise in both mechanical engineering and AI in getting all these things working together. So these are the specific challenges that we looked at. We wanted a rural-specific autonomous vehicle testing framework, something that doesn't exist that well in the digital twin asset space. And that involves, creating these new rural car maps that lets us kind of put the car digitally in a rural environment. And then there were these additional challenges which were theoretically quite interesting for us, which was, there are all these things that we know anecdotally, right? We know that there are deer on the street, there is other kinds of animals, there are all these high-speed differentials between, the car and maybe a tractor that has just pulled into the road. But if you think about how many such cases exist, that's the difficult problem, right? Because if you think of all the things, all the ways things can go wrong, then that possibility space kind of explodes and becomes too large. So we came up with this Genesis RL, which is an RL-based observer that sits on top of this whole simulation and tries to steer the scenario or the environment into these more challenging and difficult cases that are going to be stress cases for our perception system and for the car in general. And then there is another part that says that, we did all of this in the simulation space, but what about the domain transfer problem? When you have real physical cameras, real physical cars, then those learned parameters don't really translate from one to the other. So that's where this perception error model comes in. And we will round all of that up with model in the loop and the vehicle in the loop validation process that we will hopefully get to. All right, so before we go to the next one, Ali, do you want to go ahead, turn the lights off?
Yes,
Yeah.
go ahead.
So this is a video that
You can drag that screen share. You can drag that.
Yeah, so this is a video that was shot in the lab as part of a project that Ali's group did a really great job. So just click on.
Yep. Wait. Yep, wait.
Augustus J. McCann was a henpecked married man. He'd been fighting with his wife since his married life began. One night about 3:30, while out.
Since long ago, roads have carried us to our destinations. But for many, the journey still ends in tragedy. crashes change the course of thousands of lives. Can technology make the road ahead safer? Out here, the road can change in an instant. A tractor pulls from a field. A deer leaps through the fog. No warning signs, no painted lines. And while only 1 in 5 Americans live in rural areas, nearly half of roadway fatalities happen here. With the arrival of automated vehicles, road safety is expected to gradually improve. But can they handle rural conditions where roads are unpredictable, weather changes fast, and there's no guarantee of strong markings or signs? That's why the Center for Regional and Rural Connected Communities research team at the University of Tennessee, Knoxville, built a rural-specific framework for automated vehicles, blending sensing, mapping, and control systems built for these unstructured environments.
Our perception error model recreates the mistakes vehicle sensors can make, like misjudging distance in fog or glare, so that we can teach the systems how to avoid them by simulating sensor errors while bringing realism into virtual tests.
We also developed Genesis RL, a reinforcement learning tool that throws tough, realistic hazards at vehicles until we can see exactly where they fail.
These stress tests reveal exactly where the car's sensors or computer could be too slow or make mistakes in judging speed, distance, or timing mistakes that might lead to accidents.
Virtual tests can only go so far. That's why the team links a real car to a living virtual rural world, a setup called Vehicle in the Loop. Our Vehicle in the Loop is a car that reacts as if it's on an actual back road, but in the safety of a lab.
That setup gives us the realism of the road without risks and the consistency of the lab without the cost of endless test drives.
Vehicle in the Loop testing provides a fidelity that's not achievable with modeling and simulation. It also provides a repeatability and cost-effective accuracy that's not achievable with on-road testing.
With this method, the research team can investigate and solve rare but critical failures without putting anyone at risk. This work is especially important in Tennessee, where road crashes have disrupted access to schools and healthcare and caused devastating losses of lives and property.
If autonomous vehicles can solve these problems, they can provide more safe and reliable mobility options for rural communities.
Working on this project gave me real-world skills in AI and vehicle safety. And more importantly, it showed me innovation should reach everyone, no matter where they live.
Safer roads mean stronger communities, and this research is bringing that future closer. When technology meets community, the road ahead is not just safer, it is brighter.
All right. Oh, wow. That was good, didn't it? Ali, thank you very much. I mean, it did take the entire day, and the students would not want to do it again. I have been told, but it was worth it. You know, it's a wonderful representation of the task that we're doing and the challenges, and it looks neat. All right, so kind of just giving a little bit more details into what we have just seen. This is how it works, right? I mean, if you want to put an AV on the road, then you have to sense the environment, right? And the environment consists of the scene as well as these other things like weather and lighting, the pedestrians, road type. All of these get sensed, and sensing usually happens with either a camera-based system, or you have lidars, or you have radars, you have GPS, GNSS systems, all of these things, and car odometry, right? So everything works together in the perception model that gives you a sense of the environment, right? Where the other cars are, where the lane markings are. And then your path planning model comes in and says that, okay, I have to move this, right? There's a car there waiting at the intersection, so I'm going to stop, wait for it to pass, and then kind of move on. And then this information gets converted to a trajectory that gets sent to the lower level controller, and that usually would drive the car. And the whole thing would repeat, right? Now, what we wanted to do was to see how we can do all of this by having the car on a dynamometer. So we probably know what that is, but it's essentially rollers on the ground that you put the car on so the wheels can turn and you strap the car down so that it's going anywhere. But at the same time, it does use its entire hardware stack to move the car forward. It just doesn't physically move in space, just the wheels turn, right? And this is the whole pipeline as it would look if this whole thing worked. Okay, so we have the simulator, which creates the environment, it creates the digital space, it creates the RGB images. And those frames now get sent to the controller, in this case, OpenPilot. And that makes sense of the environment. It senses where the car is in respect to its environment. And it comes up with those, going through those modules that I just showed in the last slide, with the control, right? And this control now gets through the ECU into the actuators and the car actually runs. Now, if the car is on the dynamometer, as I said, it does not move in space, but the wheels turn. And that movement is translated into an actual movement of the digital car in the digital world. And that will move forward and the whole thing will continue. And for that, we need the reverse kinematics of the vehicle. In this case, it's just a simple bicycle model. Now, the whole problem, this thing is nice, but the thing is, as if you know, like if you have taken your car for inspection, some states need it every year, they would put it on the dynamometer, but usually you would only be able to go straight. Well, not go, but I mean, there's only one roller, so you would just, you would keep it steady, right? What we need to do is have a way of the car being able to steer, right? So that means while being on the dynamometer, we needed a way to transfer the motion between the two wheels, keep them synchronized, and at the same time be able to steer the front wheel so that we had the full experience. And this is where this, you heard him speak, his name is Sean Huff, he's a retired scientist from Focus National Lab, and he built this entire system from the ground up and has founded a company based on that. He came and created this system where we could do just that, which is transfer the motion between the two wheels, and at the same time, keeping a steady speed, allow us to steer the car through its entire range of motion. So now what we have is a really powerful setup, right? We can make the car do what we want, right? We can make it go along a car, we can change lanes, we can navigate intersections, and the entire situation, the digital world that it believes it is in, is something that we can create, right? So it's pretty safe because the car is obviously strapped down, it's not going anywhere. But we can put a person in black clothing in front of the car on a dark night and see if the car crashes into it, right? And we can probe each and every subsystem. Did it not see it? Did the perception system fail? Did it see it, but see it too late? And the braking was not aggressive enough. So we can just look at each and every little thing and then figure out what was the cause of that entire train of events, right? So these are some examples of the same thing happening. So in the first one on the left over here, you will see that fires on the dynamometer, you can't see the dynamometer, but it's inside the lab. And we have exposed it to a pretty interesting and
ready?
interesting event, which is it believes that there's a car in front of it facing towards the car. I mean, not an unusual thing to happen, but maybe there was a prior crash and the car turned around. And the car does go and crash into it, okay? So this whole sequence essentially kind of showcases the possibilities of what we can do.
Yeah, I'm ready.
And the next one over here, same concept, except instead of being on the dynamometer, we are on an empty parking lot. But the car AI believes that there is a car in front of it. And in this case, it does actually go and stop in front of it at a safe distance. So, it's kind of, you can think of it as an augmented reality with a very elaborate setup because the car itself is part of the controller, right? So now equipped with this, we did some really simple tests first, which is, going and stopping for a car and following a car. And we had the usual response metrics like minimum time to collision. This one is specific for us, the mean detection ratio. Essentially, it says if the car is at a certain distance, let's suppose that where the pillar is, and I believe that the pillar is where the chair is, then the detection ratio would be my belief divided by the actual distance. So, we ideally would like that ratio to be 1, which means we have a true estimate, but it can be greater or less than 1 depending on the situation. Now, if we run it, over and over for many, many different situations, I don't know if you can read it, it's kind of small, but let's say the first one, it's noon, it's clear, and there's an ambulance in front of the car. Then the second one is a sunset, clear, ambulance, and so on. If you go through the list, you see that they're kind of nicely clustered together, and we can see that the TTC is also widely varying depending on that DR, the ratio of the distances, right? Now, at 1, it is correct. It estimates the distance correctly. If you go over here, it thinks that the distance is too far. Okay, too far means it thinks that it has more space than it actually has, which means there is a chance that it will go and crash. And that's exactly what happens. You see on 0 means in these cases the car may crash into something. Now, that's the dynamics part. Now, if we correlate that with what the environment is doing, and we have these parameters, because it's simulation, essentially everything is just a knob that you can turn and make things go, back and forth, right? So let's suppose I have a knob for the fog percentage. The amount of fog that is in the scene is going from 0% to 100%. So fully clear to fully foggy, you cannot see anything, right? And we can kind of see the DR, the ratio of the distance kind of getting higher and higher depending on how much fog there is in the scene. Now, these actual numbers do not mean much because this fog percentage is just an attribute of the simulation, but there is a physical equivalent to that, obviously, that we can do with more testing. Now, this red line says that, okay, if you have fog and the car is going to struggle a little bit, but it's still okay because it's not going to crash into anything. Beyond a certain percentage of fog, it becomes devastatingly dangerous because it's going to think that the car is either not there or too far away or see it too late and it's going to crash. So there's a relation, pipeline between this, where we are looking at the perception system, its understanding of the scene, and then what causes that. And all of that is essentially going to dictate how we either retrain and train it better to deal with these situations, or have other ways of either telling the driver that it's time to take over control, things like that. We did another experiment with the sun angle because that's the beauty of simulations. You can just change any parameter that you want, keeping everything else the same, right? So you can do more and more and more tests, and you get more and more data. And there are some certain meanings that you can make out of it. So that is the advantage of simulation, but also the disadvantage because of all these infinite possible variations that we can bring to an environment. Which ones should we do, and which ones doesn't need to be done? So that's where this whole idea of Genesis RL comes in. It's essentially this deep reinforcement learning agent that sits outside the entire simulation, and it has control over those knobs that we just said, that the one that changes the world in the simulation environment, right? And this VRL agent's job is to make it as difficult as possible for our car AI to be able to function, right? So what it does is now it finds a narrow path through this entire possibility space and hones in on those situations which make it really difficult for the car to operate. So it essentially goes sequence by sequence and finds this combination of parameters that makes it really difficult for the car to operate, those stress spaces. It's kind of like a more automated and quantitative way of finding the really difficult situations. And we used the violation scores in the rule book to kind of score how we did. Instead of thinking sequence by sequence or system by system, it's not like the perception system only that we're looking at. It's the overall effect of those errors cumulatively and how much a violation it does to a proper driving rules. So as we can see that the system with the Genesis RL policy has more success in failing. That's a weird way of saying it, but the more we fail to do well or drive well means that we are better in terms of finding those edge cases that makes it difficult. So we did well there. Now the last part of this discussion would be on going from this whole setup, which has camera images that are synthetically produced, to real world data and how we can bridge that gap. For that, we had this crazy idea. Well, I didn't. My student did. Graduated. That was his kind of main contribution to his dissertation, where he said that, hey, we have simulation, which means we have a perfect knowledge of the ground truth, right? We know exactly which pixels my car occupies, right? Let's suppose, I know exactly that the green is the real boundary for the vehicle as seen from this angle. But the perception system makes errors, right? And it may completely miss it, it may misclassify it, or in most cases, it would not know exactly where it is at. Maybe it's shifted, right? So that X is the gap between the real and the perceived, right? The question is, can we model that error as a function of a myriad of different conditions, right? So can we teach a deep learning model to be able to learn how that error evolves with nighttime versus daytime, distance, speed, rain, fog, etc. So if we have real data and we have ground truth, we can now just take the ground truth, apply that error, and then have a realistic representation of how the perception system will behave. So we use that. We got a bunch of results. It looks good. The error is, very, very tightly coupled with real data when we are using the PEM model. And it does better in terms of, just randomly sampling the error from a Gaussian distribution. We try different kinds of distributions. And we actually had to invent a new type of deep learning model for this time series data generation called FETSGAN, which was another thing, but that maybe too complicated to get into it, with a short time. But combining together FETSGAN and PEM does a really good job. The last thing is just a snapshot of some of the things that we tried out, in the rural setting that we created with Varda. We didn't have a tractor, but we put an SUV in it, and we kind of had this simulated environment of, cornfields and unmarked roads, and we tested different kinds of things. And, the solutions and the results and the performance of the perception system kind of validate our ideas of how different kinds of environmental variables do indeed contribute to different errors, system-wide, but also subsystem-wide. So those were the findings. We would like to acknowledge support from CTR and of course from CR2C2, and that will be my talk. Thank you very much.